Hello, welcome back again. Today we're looking at the 1986 AIME problem number 7. The problem is that we have a sequence of numbers, increasing integers, 1, 3, 4, 9, 10, 12, 13. And these are the positive integers which are either powers of 3 or sums of distinct powers of 3. Okay, and notice that we're including 3 to the 0 as a power of 3 because we have the number 1. Okay, the question is, what is the 100th term of this sequence? Okay, might want to try this puzzle out on your own before I show you how I solved it. It is I think a pretty unique way of solving this problem. Anyway, so let's get started, show you what I did. First, let's explore these numbers. Okay, so 1 is 3 to the 0, 3 is 3 to the 1, 4 is 3 to the 1 plus 3 to the 0, 9 is 3 squared, 10 is 3 squared plus 3 to the 0, and 12 is 3 squared plus 3 to the 1, and 13 is 3 squared plus 3 to the 1 plus 3 to the 0. So these are the first 7 terms of the sequence, and you can see that the pattern is that you either include or don't include each power of 3. Here we're including 3 to the 0, this doesn't, this one doesn't, so on. In fact, if you look at what powers of 3 you're keeping or not, we can make a little table, like are we keeping 3 to the 0? Yes. Are we keeping 3 to the 1 but not the other 2? Yeah. Here we're keeping the 1 and the 0, and here we're keeping the 2, and here we're keeping the 2 and the 0, and you may begin to see a pattern forming here. If you change the check marks into the number 1s, this would be binary for the number 1, 2, 3, 4, 5, 6, 7, and so on. Okay, so in other words, what we can do is we can think of our number and write it as a binary number. So for example, 12 is 3 squared, 9 plus 3 to the first. Okay, we're going to translate that into the binary number 1, 1, 0, base 2. But really this is 3 squared plus 3 to the 1. So these are supposed to represent powers of 3. So what we can do is we can then recast that base 3. And then that base 3 is equal to the original 12. Okay? In other words, every one of these numbers you can write as a base 3 number, but only using the digits 0 and 1, which is what you'd normally see when you're counting in base 2. Okay? Therefore, let's look at the number 12 is the 1, 2, 3, 4, 5, 6th number on the list, and the number 6 in binary is 1102. Now change that to base 3, calculate what that is base 3, and then you have the 6th number on the list. So now we have a procedure to find the 100th number on the list. So take the number 100, rewrite that in base 2. Let's see, that's 64 plus 32. 64 plus 32 is 96. So we need 4 more. So we don't have 16, we don't have 8, we have 4, we don't have 2, we don't have 1. Okay, so that's our number base 2, 1100,100 base 2. Okay, change that into base 3. So 1100,100 base 3. Calculate what that is in base 3. So this is the 0th power, 1, 2, 3, 4, 5, 6th power. So 3 to the 6th plus 3 to the 5th plus 3 to the 2 equals, then I have to, okay, so this is 729 plus 243 plus 9, which is 981. So the 100th term in this sequence is 981. So I thought this was an interesting problem because you get to use multiple different bases and sort of bounce between the two in order to solve the problem. Anyway, I hope you enjoyed the video and hope to see you in the next one. Have a good day.